Hello and welcome back. This lecture is going to cover the topic of underwater weighing and how we can use that technique to actually estimate our body fat percentage. So we're going to go way back to Archimedes' principle to start this one out. And we're going to look at how we would calculate the density of gold and silver to start. Overall, we know that our density is going to be our mass divided by our volume. So that's pretty easy if we're looking at just a block of gold that happens to be, 10 centimeters by 10 centimeters by 10 centimeters. We could put that block of gold onto a scale and find out that it's about 19,000 It's about 19,282 grams. Now, since I already said that it was about 10 centimeters by 10 centimeters by 10 centimeters, we just multiply those out, and that gives us 1,000 centimeters cubed. Okay, as we've already discussed, our density is just our mass, 19,282 grams divided by our volume, 1,000 centimeters squared, and we get our density of gold at 19.3 grams. Pretty simple stuff. Okay, next step would be silver. Well, we could take a block of silver about the same size, 10 by 10 by 10 centimeters, put it on a scale once again, and find out that that's about 10,500 grams. And if we look at the volume of that, 10 by 10 by 10, still 1,000 centimeters cubed. Well, we do the same division there, mass over volume, and that gets us our value of density, which is 10.5 grams per centimeter cubed. Same up here. So, we have our two densities, 19.3 grams per centimeter cube and 10.5 grams per centimeter cube. Well, in the story about Archimedes' principle, what happened was a crown was presented to a king, and he assumed that it was all gold. However, the metalsmith who was working on it was a little bit shady, and he brought in Archimedes, his revered scientist, much like everyone in this class, and he said, I need a way for you to figure out if this crown is actually fully gold or not. So the first thing that Archimedes did was he weighed the crown and found out that it was about 15,000 grams. And if we knew the volume of the crown, if it had easy to measure dimensions, we could just calculate the volume. It would be a simple way to determine the density of it. However, he couldn't measure the volume of it because, as you can see in the picture, a crown has a lot of twists and turns in it. It's going to be hard to calculate what the actual volume is. So the story goes, one day in a bath, when he sat down, he noticed the water rise. He said, Eureka, I found it. And he was able to say that if you were to submerge an object with irregular sides, the volume of the water that it displaced is going to be equal to the volume of the object itself. Fantastic. So by placing that crown into a tub of water that was filled to the very, very brim, allowing a basin outside of that to catch the water that spills out, once the crown is submerged, they were able to say that, the amount of water that spilled out happened to be exactly 1 liter. This is just for our example. And we know that 1 liter in water is about equivalent to 1,000 centimeters cubed. Very convenient. So therefore, if we were to once again calculate our density of this crown that had a mass of 15,000 grams and a volume of 1,000 centimeters cubed, we would find that the density of it is then 15 grams per centimeter cubed. Aha! So Archimedes was able to go back to the king and say, well, the density of this crown is not consistent with gold. It is less dense than the gold. It is a little bit more dense than the silver, so it happens to probably be a combination of the two. If we wanted to go into that and figure out exactly what percentage that would be, well, we would just say, okay, the percentage of gold times our density of gold, 19.3, plus 1 minus the percent gold. We're assuming here that it's only gold or silver. That would be multiplied by the density of silver, 10.5. That would get you your density of 15. If we were to solve this equation and extrapolate it out, what you would see is you would get about 51% gold and about 49% silver from that calculation right there. And that is going to come into play in a few minutes, because the next step would be, all right, when I bring people into my lab, when I'm measuring people as part of a fitness program, we're not talking about crowns here, we're talking about people. So how would we use our underwater weighing, how we submerged our crown before, to be able to then calculate body fat percentage? Well, it starts right up here with this picture. You can see an individual sitting in kind of a cradle in the water with a scale on top. So how will we do that? Well, all we want to do is be able to calculate our density once again. So if we want to calculate mass, that's the easy part. Let's use the example that they have in the book. We have a football player who's 121.73 kilograms. Once again, we're trying to find out what their volume is. We have an irregular shape, and when you have a person in the lab, it's not as simple as being able to catch just the amount of water that comes out. Imagine if you had 2 or 3 people that you had to do that with. You'd have to consistently keep refilling your tub. So we use a different technique. In order to get our volume, what we're going to do in this case is we are going to say that volume is going to be equal to our mass in air minus your weight in water to start. And why do we have that? Well, if you think about it, when we have any sort of force, we also know that there is going to be an equal and opposite force associated with that. Go all the way back to physics. So if we have an object, in this example, a person who is being submerged in water, even though they are more dense than the water in itself, they're going to sink. The difference in their weight between what they weighed in air and what they weigh in water is going to be equal to that upward force on them. So we don't necessarily need to measure the volume that they are displacing like we did with the crown before. We just need to measure the difference in weight. However, if we take the example and we say we're going to start with our, let's go up here, 121.73 kilograms, and we're going to subtract from that the weight on the scale once the person is completely submerged. The example in the book gives 7.3 kilograms. That would give us a weight in, or a difference of 114.43 kilograms. But remember, we're still trying to get to volume, so we need to do a conversion. Well, we know that we could just multiply this. If we want to cancel out our kilograms, there's 1 kilogram for 1 liter of water. However, this is only true for the density of water when the water is about 4 degrees Celsius. So if we want to make our participants a little happier, we're going to need to raise that water temperature up, and this 1 kilogram becomes about 0.993. And this is going to be dependent on the water temperature that you're using. So I'm just using the example that's in your textbook. Now, if we do this, our kilograms cancel out nicely, and what do we get for a volume? That's going to be 115.24 liters. Our kilograms have canceled out. Now, we need to do one last step in order to fill in this box over here. We have the volume of the person, but we have forgotten about one very important compartment. When that person sits in the chair, they're going to breathe out all of their air. Even if you breathe out everything to your voluntary exhalation maximum, you're still going to have a certain volume of air called your residual lung volume. So from our 115, we then need to last subtract our residual lung volume, RSL, and in the example in the book, they give that as about 1.213 liters. Whew. So now, if we do all of this, we can go back and say that our volume for our 121 kilogram football player is going to be 113.98 liters. If we do the division, our mass, 121.73, divided by our volume, 113.98, that's going to give us a body density of 1.068. Whew. Now, if you look up at the title of the slide, we said we were going to talk about underwater weighing and body fat calculations. And I know you're probably saying right now, you haven't told us anything about body fat. All you've told us is that this person's density is 1.068. But if you think back to the beginning of this little video, we talked about how we could determine the percentage between silver and gold, right? By using this little equation right here. Now, we don't have to do exactly the same thing, but Dr. Siri, back in the 1950s and 60s, came up with an equation that can help us out. All we need to do is take to determine our body fat percentage. It rests on this right over here, a two-compartment method, where we say fat is going to have a density of about 0.9, and everything else is going to be considered FFM, fat-free mass, skeletal muscle, organs, remaining soft tissues, and minerals. We're going to say all of that together has a density of about 1.1. And if you look, our density of our football player is between 0.9, so he's not 100% fat, but it's also less than 1.1. So we need an equation to help us bridge the gap between this density and these two values right here. We don't do exactly what we did with the gold and silver, but what we will do is we will take a constant and determine that body fat is then going to be equal to 495 over our body density, which in this case is 1.068. And then from that, you're going to subtract the constant of 495. All in all, if we do everything right, this will give us a body fat percentage of about 13.5%. Congratulations, you've made it to the end. Now you know all about Archimedes' principle, how to discover the density of a substance that you don't know what it is made of, and last but not least, and the most important part, how when you take a person's weight in water, using this method right up here, you can then calculate their density and use that density to calculate out their body fat percentage. Thanks, and I'll talk to you later.